In this second part of the lecture, let's look at a variant of the marching cubes algorithm. We saw that the marching cubes algorithm essentially uses a case table. It looks at each voxel, classifies the voxel into one of 256 different configurations, which are reduced to much fewer number of configurations based on symmetry. So in this case, Greg Nielsen has reported 15 different cases. Once a particular case is identified, then the case table essentially gives a template for the isosurface lying within the voxel. So we saw that in the case of a single positive and 7 negative, we had 3 isopoints and the isosurface consisted of a single triangle. We saw isosurfaces for a few other configurations as well. The number of triangles constituting the isosurface could vary from 1 to 2 to 3 and in some cases 4 and 5 also. Here are a few more cases that we saw in the previous part of the lecture. So all the cases seem to be working well so far. We did not talk about any issues with the algorithm. However, this marching cubes algorithm, as stated, had a major flaw. While the algorithm was simple and in that sense elegant, it did not guarantee that the surface that it produced was correct. For example, if we consider the pre-image of a function, so if we look at f as a scalar field and look at its pre-image, so let's say f, and its pre-image, if f is a three-dimensional function, then we know that the pre-image is a surface. However, the marching cubes algorithm does not guarantee that what it produces is a surface. In some cases, it could produce intersecting surface, self-intersecting surfaces, or surfaces with holes, objects that are not even surfaces, and so on. So here is one such example where the marching cubes algorithm breaks down. The shaded vertices correspond to the, let's say, the plus vertices. So in the left we have 3 plus and 5 minus, and here is one particular template from the case table consisting of 3 triangles for the isosurface. The voxel on the right, let's assume it is adjacent to the voxel on the left. So they share a common face. The voxel on the right has 6 plus vertices and 2 minus. So its isosurface consists of 2 triangles. The 2 triangles come from the various plus minus edges due to these 2 minus vertices and these corners. Now it's already clear that there is a mismatch between the isosurfaces that was extracted for the 2 voxels. The voxel on the left, if you look at the isosurface that comes from the template, it gives an edge such as this, And for the same phase, the voxel on the right says that the isopoints have to be joined in this alternate way. So this is already an ambiguity that needs to be resolved. So there is a mismatch. If we look at the common phase, while the plus signs remain the same, we have that each voxel identifies a different way of connecting the isopoints. Let's look at what happens when we make the two choices in a 2D case. So here is the same example that we saw earlier, and here one of the squares contains this plus minus configuration, where the endpoints corresponding to the diagonal are positive and the other two endpoints corresponding to the second diagonal are negative. So depending on the choice that one makes, one gets different isosurfaces. So here is so here is one example with such a configuration. So let me point that out. So here is a plus and another plus, and the other endpoints are minus, as you can see. Now, depending on how the isopoints are connected, we either get a connected isocontour, such as what we have here, or something like this, where the isocontour splits into two components. Note that this local decision caused a change in the global connectivity. The Marching Cubes algorithm's beauty is in its simplicity and the ability to restrict all computation to the individual cell. However, this comes at a cost. We are no longer able to guarantee global connectivity. So here is the problem again. With such a configuration of two plus along the opposite ends of a diagonal, we get 4 isopoints and hence two different ways of connecting the isopoints. Now all is not lost. There are ways to locally fix this problem, and that is what we would like to study. But before that, let's go back and see how this problem appears in 3D. So this was one of the situations where we could have a mismatch. So due to the 2 plus, we may want to construct the isosurface such as what is shown on the left, or the case table could have a template as shown on the right. The question is, how do we decide which template to choose? So in order to fix this issue, we need a consistent way of connecting the isopoints. And if we do this, then we get a match for the adjacent voxels and all is fine. Like I mentioned, there are many solutions available, and in fact, among these solutions, there are several that work within a local neighborhood. In fact, they work within the voxel in order to fix this apparently global issue. One such solution was proposed by Nielsen and Harmon, and it's called the Asymptotic Decider. This solution came within a couple of years of the Marching Cubes algorithm paper. The main idea behind this method is to consider bilinear interpolation within the faces. So if the function sampled at the end vertices of a face is b sub 0, 0, b sub 1, 0, b sub 0, 1 and b sub 1, 1, then the value of the scalar function at a point st is given by the expression that you see on the right. You can see that the weight associated with b sub 0, 0 is equal to 1 minus s times 1 minus t. The isocontours for this particular scalar function is a hyperbola. So you can convince yourselves about this fact. So the isocontour is the set of all points st such that b of st equal to a given constant alpha. So we all know how hyperbolas behave. So here is a picture of the isocontour together with the 2D cell to the face that we are considering. Let's assume that the two endpoints that we are seeing are the plus vertices. The hyperbolas that you see here are the two components of the isosurface passing through this particular face. So how exactly the hyperbolas go through this cell really depends on the values of the function on the corners. So there are multiple cases possible. The axis here is actually the asymptotes of the hyperbola, or the axis of the hyperbola. So of course we care about the case where the origin of so the meeting point of the two axes is contained within the box. That's when you have the configuration of plus plus along one of the diagonals. So the particular configuration that corresponds to our case can be easily identified simply by identifying the location of the origin. Now, what exactly is this origin? The origin is essentially the is given by the asymptote of this hyperbola, which is obtained by looking at the saddle value. So before going there, let's look at this asymptote, and let's say that the asymptote corresponds to a particular S and T value. So we compare the value at the asymptote with the value that is given to us, which is alpha. Now comparing these two, we can decide how to connect the isopoints. So in this example, we can see that we have the isopoints here. So these are the 4 isopoints, and we have the plus. So how does the isosurface, the isocontour behave? Let me draw a picture on the right for the same configuration to avoid clutter. So I have the 2 plus, I have the 2 minus. So let's look at a sequence of scalar values. and the corresponding isocontours restricted to this square. So let's say we pick a value that is above the two minus vertices. By above I mean the function value, the iso value is greater than the value at the two minus vertices, but below the function value at the two plus vertices. So the isocontours would initially look like that. So they will always have two components. The next isocontour, let me draw that as dotted, would be like that. And the next one may also be like that. You can see that these two contours will meet, and that is exactly the asymptote. Once they meet, so once you hit the so-called saddle value, then again you have two components, but now the isocontour gets connected like that, and then so and then leaves the box. So clearly we would like to compare the value of the function at this saddle point corresponding to the asymptote with the isocontour in question for this particular, so we want to compare it with alpha, which is the input to the Marching Cubes algorithm. So if alpha is less than the value at the saddle, then we know that these are the negative coordinates, the negative vertices, and so we would like to connect the iso points such as this. The other case is where alpha is greater than the value of the function at S alpha T alpha. And for the four iso points, we again connect now the iso points like this. So note that we are using straight lines to connect the iso points, whereas we do know that the isocontour is a hyperbola. So here is already a visual, well, not really an evidence, it's just a visual illustration of the fact that what we are computing is a linear approximation of the isocontour or the isosurface. The question that remains is, how do I find S alpha T alpha? Well, this can be computed just by recognizing that this is the point where the partial derivatives go to 0. So considering the expression for B and setting the partials to 0, we can obtain S alpha and T alpha, and plugging those values into the expression for B, we get that B of S alpha T alpha is this expression. So we know B of S alpha T alpha in terms of the function values at the four vertices. So with that, we are done. So let's analyze this algorithm in terms of the running time. So clearly the Marching Cubes algorithm has to process every voxel, and it reads every voxel and processes it in one shot. So it clearly takes linear time in the number of voxels or the grid cells. The time taken to process each voxel is constant time, essentially a lookup from the case table. So the algorithm running time seems to be competitive linear time, what more can one ask for? But we have to be careful here. So this runtime is linear in the number of grid cells. However, the what we need to note is that the isocontour or the isosurface in 3D need not pass through all grid cells. Often the number of grid cells that contain the isosurface is much smaller than the total number of grid cells. So this is not necessarily a good algorithm in terms of running time. However, the algorithm is amenable to parallelization. So this is one reason why it is competitive in practice. In fact, there are GPU implementations also available. So I talked about output size, the number of triangles that come from the isosurface. So here is another aspect of this. So every grid cell contains at least two triangles corresponding to the isosurface. The size of the output really depends on the number of cells that contain the isosurface. The question is, can this be reduced? From a first look, it seems like this is impossible. You have to consider every voxel that contains the isosurface. So how can we even reduce the number of triangles that you report for the isosurface? We will talk about this at the end of this lecture. What if the input is not a grid cell but a collection of tetrahedra, as in an unstructured mesh? How does this affect the output? Naturally, one can think of a marching tetrahedra, a variant of the marching cubes, where you march through each tetrahedron and report the isosurface. How does this affect the number of isosurface triangles? Is there ambiguity? Is that an issue here? What about runtimes? So these are all valid questions. Again, we will talk about marching tetrahedra very briefly in the next couple of slides. To summarize, we talked about ambiguity in the marching cubes case table. This ambiguity arises in 2D as well. In fact, there is only one ambiguous case in the marching squares problem, the 2D version of the marching cubes. So the problem here is, how do I connect the iso points? The solution from the asymptotic decider works here beautifully. Marching cubes has several such cases. The asymptotic decider is able to resolve all of them. There are still some issues though that the asymptotic decider is not able to resolve. So this was studied in the following years and essentially resolved in the early 2000s. So the 2003 paper and 2004 there was a few papers that put this question to rest finally. So often the solutions for this ambiguity problem was resolved by assuming some underlying function. For example, bilinear or trilinear interpolation, or some assumption about the connectivity of the voxels, either in the interior of the isosurface or the exterior of the isosurface. In the reading, I have uploaded a survey on marching cubes that talks about the different proposed variants. This is just for additional reading, not the primary reading. One algorithm that is an obvious variant of marching cubes is the marching tetrahedra. The number of cases is much smaller here. We have only two cases. The case where one of the four vertices is plus and the other three are minus. So here we have the case table for the two cases. For the first case, we have a single triangle. the second case with 2 plus vertices, we have essentially a quad with 4 vertices. So we have 2 triangles for the isosurface. No ambiguity in either case. This is a linear interpolant. There is no ambiguity at all here. The isosurface is linear, and it is not even an approximation. It is an exact isosurface for the piecewise linear function. Since the domain is now decomposed into tetrahedra, the number of cells in the domain would naturally be more than the number of grid cells. So this leads to an increase in the input size and hence an increase in the number of isosurface triangles. There are many ways to convert a grid into a collection of tetrahedra. One popular way is to divide it into 6 tetrahedra. There is a way to subdivide a cube into 5 tetrahedra. However, this does not lead to periodic conditions. So one has to then worry about how exactly the neighboring cubes are subdivided so that their faces match with each other. To avoid this issue, we often subdivide a cube into 6 tetrahedra. How do I reduce the output size? Well, one way is to reduce the size of the input grid via sampling. Another way to reduce the size of the output is by computing so-called multi-resolution surfaces. If time permits, we will talk about this in a separate lecture. But this is an interesting topic in itself. Representing an isosurface using fewer triangles while trying to reduce the error introduced due to the simpler representation. So what you can see here is a high resolution isosurface. The same surface is represented using fewer and fewer triangles here above. You can see that the overall features are still captured in these isosurfaces. So this is a topic that was studied extensively again in the early 2000s, and the problem is more or less solved now. We do still see a few papers appearing on this topic within the graphics community. Another problem that's related to the topic of today's lecture is efficient rendering of the isosurfaces that are extracted. So clearly one iso value gives you one isosurface. So if we want to display multiple isosurfaces, we may have to use transparency so that we can see through and study multiple isosurfaces. Several papers discuss such renderings of multiple isosurfaces. Rendering an individual isosurface could also be enhanced via a careful choice of lighting and shading algorithms. So this has also been studied extensively. So with that, we come to a close to this lecture on matching cubes algorithm and a simple variant that guarantees correct results. In the next few lectures, we will talk about variants of the matching cubes algorithm that improve the running time.